Good morning. So, I don't know how many of you actually solved the problems, but let us try to solve them here. So, in the first question, in how many permutations of the word mobile do the expression MO exist, but MOB does not? Okay. Okay, so how do you think about the problem? So, I have a word, mobile. If I want to look at all permutations, of course, the problem is simple. 1, 2, 3, 4, 5, 6 factorial. Yes, but I want to find the number of permutations in which you see MO exists, but MOB does not. So how should I think about the problem? Do you have any ideas? So for example, let us say that this rectangle shows all permutations. Yes? Okay, and then when I look inside, some permutations have MO in them, some permutations have MOB in them. So let me try to draw circles around those items with MO and around those items with MOB. Okay, how do you think I should draw? Because you know that if in the language of set theory, I want to draw a circle representing one set, the set of all items with MO in them, and I want to draw another circle representing all the items with an MOB in them. Yes? In principle, potentially I can draw circles completely outside. I can draw circles in a way that they intersect. I can draw one circle within the other circle, something like that. So that's what I'm asking you. Which one do you think will be? For example, let me write A be the set with MO in them, and let me say that the set B consists of all permutations with MOB in them. I want to draw a Venn diagram for it here. So how should I draw them? Yes, Ebri? A inside the B, so it means like this. This is A and this is B. This is what you are saying, yes? So in other words, you are saying that A is a subset of B. This is what you mean by writing it in this way. So is that true? What he means is that if you have an item here, that item is definitely here. Is it obvious or not? Because if an item is here, it has MO in it. Yes? Is it guaranteed that the item is also here? Are you sure? Yes? It's the other way around. Yes? Because if an item has MO in it, still it is not guaranteed it has MOB in it. Yes? So it should be the other way around, yes. So this should be B is a subset of A. Yes? So this means that B should be here and A should be here. Yes? This is just imagining this. Whenever it comes to complement principle, it's better to draw a Venn diagram. It will help you to understand better. Okay, so now where do I want to count? There are some elements inside this rectangle. Okay, some of them are within A, some of them are within B, some of them are in between. So what is the target of this question? They are asking about those items that contain MO but does not contain MOB. So do you agree? We want to count the number of elements here. Do you see that? Yes, because whatever is here is inside B, so it contains MOB, and it is not here, so it does not contain. Sorry, did I write it the other way around? No, B should be a subset of A. Yes, so this is. I forgot to change them. So this is B. This is A. Yes, so if I pick an element here, this element is inside A, so it has MO in it, but it is not inside B, so it does not have MOB in it. Yes, that is exactly the ones that the number of items here is the number of items that I want to count. But isn't it obvious? How should I do that? The number of elements in this rim is what? The question mark is in principle the number of elements in A minus the number of elements in B. Is that right? Okay, but now let us count the number of elements in A. What items are in A? All permutations in which M and O are next to one another. And this is a very standard problem. You know how to count it, yes? So for example, you can imagine a box that you put MO in it, yes? And then you have other items, B, I, L, E. So how many objects you see now? 1, 2, 3, 4, 5. So the number of items here is just simply 5 factorial. Yes? And now, the number of elements in B, it means that I am looking for those. Be careful, I am not allowed to multiply it by 2 because of 2 factorial, because I want to have it MO in this order, not OM. I want to have MO. So there is no 2 factorial because of permutations here. And now here I want to have MOB together. So that is also easy, yes? What do? I will construct a box with MOB in it in this order, and then I have I, L, E, I can permute them. 1, 2, 3, 4 objects. So here there are 4 factorial objects. Okay, so 5 factorial, if you calculate it 1 times 2 up to 5, it's 120, and this one is 24. If you subtract them, it becomes 96, so the correct answer to the problem is 96. Which in this case is this option. Understandable? So this diagram sometimes really help you to understand the problem from a better perspective. Okay, so now let us go to question number 2. In how many permutations of the word mailbox are the letters M and A adjacent, but the letters B and X are not? Okay? I can give you a little bit of time. In principle, you should have already done these problems. But let me give you a little bit of time at least to read the problem and understand what the problem is talking about. And then we will discuss it here on the board. Okay, could you do it? So how should you think about the problem? So one way is just looking at this complement principle again, and this Venn diagram is a good idea. Okay, might be for this one there is also an alternative way of solving that we have already discussed. Let us see how it goes. So what I want to do, I want to just draw a diagram for myself. I would say that these are all permutations. Yes. So, of course you know that, you can imagine that every permutation of this word is another word, is a dot here in this rectangle. Every dot represents a permutation. But some of these permutations have the property that M and A are adjacent. So let me draw a circle here and call it A. In A, I will call that this one A. M and A are adjacent. Okay? In some of them, B and X are adjacent. Okay? I want not adjacent, but let us keep it for the time being, B and X to be adjacent. Okay? So this one is also B. But I want you to understand that, is that understandable for you that I have to draw them in this way? So B is B and X adjacent. Yes? I myself define A to be that one, but I will define B to be B and X also adjacent. Okay, do you agree that I have to draw them in this way? Because first of all, this is not one of them is within the other one. But of course, I cannot draw them completely separately. I cannot draw them as disjoint sets because there are some items in which both M and A and B and X are simultaneously adjacent. So it means that there is an overlap between these two sets. Okay? So, but which part of this question, which part of the diagram is actually wanted in this problem. I want to be within A, yes, so because I want to have M and A adjacent, but I want to be outside B, because if I am also inside B, B and X will also be adjacent. Is that right? So in principle, where should I count it? I should count this part. I should count the number of items here. Is that understandable? Okay. So what is this from set theory point of view? You know that in set theory, this is just A minus B. So what I am asking here is the cardinality of this set. And the cardinality of this set we'll study. Of course, it is also very clear from the diagram, is the cardinality of the first set minus the cardinality of the intersection of these two sets. This blue part is the whole circle of A minus the intersection, the overlap. Okay, but now you should interpret them. So this I should count. This is an extremely easy problem. When you want to count the number of elements here, just read what is the property of the items there. M and A are adjacent. Isn't it a standard problem? Yes. M and A are adjacent. So what do I do? But be careful. They are saying adjacent. They don't say which one comes first, which comes second. So you have to consider two alternatives. Yes. So I keep a box, and I put M and A in this box. Okay, how many options I have for putting M and A in my box? 2 factorial, which is 2. And then M and A is eliminated from my list 1, 2, 3, 4, 5 letters. I, L, B, O, X. Then in total, how many objects I have? I have one box, and then I have some letters. 1, 2, 3, 4, 5, 6. Is that right? So if I want to answer the question here, it is 2 factorial because of the number of permutations of M and A inside the box, and then multiplied by 1, 2, 3, 4, 5, 6 factorial, because then I will have also 6 different objects, so I can write. Is that clear? So that is the first one. The second one is the intersection of A and B. But read it in words. Can you read what are the properties of the items within A intersect B? What is the meaning of it in English? I am looking for the items that are inside A. It means M and A are adjacent, and simultaneously inside B means B and X are also adjacent. So what should I do? Then how many boxes I need this time? I need one box for putting M and A there. Yes. In how many ways I can put M and A here? A 2 factorial one. Yes. And then I need another box to put B and X there. Again, I can arrange it into factorial way. So what are the letters left for me? M and A are used. B and X are also used. ILO. Yes, this is ILO. So how many objects I have in total? 1, 2, 3, 4, 5 objects. So the answer to this part becomes what? A 2 factorial because of the arrangement of B, M, and A. Another 2 factorial because of the arrangement of B and X. And then 1, 2, 3, 4, 5 factorial because of the arrangement of these 2 boxes and the other letters among each other. So hopefully you understand that this should be the answer to the problem. Of course, if the calculator is allowed, you can use the calculator, but that is a very simple one because 6 factorial can be written as 6 times 5 factorial, but that's 6 times 2. It becomes 12 times 5 factorial. And this one becomes minus 4 times 5 factorial. Sorry, this is factorial. Yes? And the answer becomes 12 5 factorial minus 4 5 factorial. It becomes 8 times 5 factorial. But 5 factorial is 120. You multiply it by 8, so it becomes 960 items. So that is the solution to this problem. And as you see, we have to choose this option. But is there any other way to solve the problem? Now it comes to my mind that we can solve the problem slightly differently, not using, here I am using somehow the complement principle. The number of items that I am looking for is the total number of items minus the number of items that I don't want. This is more or less the idea behind the complement rule. Yes? But is there any other way to solve this problem that I'm not using the complement rule? Just by product rule. This is the reason. This is also a standard problem. I think you should be able to do that. So how should I write it? I want M and A be adjacent, but B and X not adjacent. Okay, do you remember I told you a trick to solve these kinds of problems? My example in the class was there are 10 people, but 2 people don't want to be next to one another. Of course, one way we solved the problem was exactly the complement principle, but I also gave you an alternative, which is a more elegant way to do it, because if you want to use the complement principle, if there are 3 people, 4 people hating each other and they don't want to be next to one another, that strategy of the complement rule becomes a little bit more complicated. But the other strategy that I told you is actually working easily. So that's why those examples that I solved during the lesson, you need to take them as some kind of models so that you can try to compare them when you want to solve a new problem. Okay, so what was the method? Do you remember? So I would say that let me count the number of elements within A. And then I do not want to consider B and X at all. So what are my letters? My letters are M, A, okay? Forget about B and X. B and X, they don't want to be next to one another. What are the other letters? I, L, and what? O. You agree? But of course, B and X are somewhere that I want to take care of them later. So let me only consider them, and let me do them in a way that M and A are always next to one another. So how can I solve the problem? Very easy. Because I want to put M and A in the box. In how many ways I can arrange them within the box? 2 factorial cases. And then 1, 2, 3, 4. Yes, is that right? I have multiplied by 4 factorial. Yes? But let us say that this step is done. This step is done. It means that I have a box. Don't look inside. And then you have somewhere I, somewhere L, somewhere O. But do you remember I have some empty spaces? Yes? These empty spaces are the good places for having B and X in 2 of those places. Is that right? Because in any way that I put B and X only in these empty spaces, I achieve my goal. So the goal is that B and X are not next to one another. Okay, but what kind of model is that? Do you remember? These boxes, these X's, even though I cross them with the same symbol, but they are different, yes, because this is the location to the rightmost location. This is the second one. This is the third one. So these are indeed distinct locations. And then I have 2 marbles. I want to put 2 marbles inside 1, 2, 3, 4, 5 distinct locations. Yes? So that's that problem. So do you remember what was it? I need to write P, okay? And then 1, 2, 3, 4, 5, and then 2. Yes? I want you to understand, so this is not probably a good idea. So let me write x1, x2, x3, x4, x5. Because in principle, x's are different. x1 is the first empty space. x2 is the second empty space. So this box should be labeled, for example, with 1, and this box should be labeled, for example, with 2. So these are distinct boxes. I have 5 of them, but I have only 2 marbles. I want to choose I want to put these marbles within the boxes so that each box receives at most 1. Yes? And that is exactly one of those abstract models that I told you to remember. So if I have done it right, this should also be the answer. Okay? Without using the complement rule, only using the product rule. So let us calculate. So what is this one? So let me write 2 factorial is 2, 4 factorial I write 4 times 3 factorial, and then instead of this one, do you remember the formula of 5 factorial on top? The difference between them 3 factorial in the bottom. And this one and that one are gone. So this becomes 8 times 5 factorial. So 5 factorial is 120, so it becomes 960 again. So these two models, it's good to remember, the complement rule model and this distributing marbles within the boxes. Yes, please.
But we can also use this for, let's say that we have another constraint that says that more letters are supposed to be not adjacent to one another.
Yes. So yes, none of them, of course.
Yes.
Yes. This can be easily done, but the complement rule will be very harder to apply in that case. Yes. But that is why this is more elegant. Yes. So but this is not easy to come to mind if you don't remember something, especially during the exam. So that's why I'm saying that those problems we solved during the lesson, in the lesson of combinatorics, these you can consider them as some kind of prototype example, so that you can have in mind and compare other problems with those problems to be able to solve them. Okay, so now let us go to the next problem. In how many permutations of the word universal does exactly one letter exist between U and I, and exactly one letter exists between A and E? Might be this is one of the hardest problems in this set. So I want to give you a little bit of time to think about it yourself, yes? So we have the word universal. In how many permutations? There is exactly one letter between U and I, and there is exactly one letter between A and E. Okay, it's a good problem. I want to give you a little bit time to think about it yourself again. Any ideas? You should have some kind of idea, yes? How do you start solving the problem? First of all, do you think there are more than one scenario going on, or no? There is only one scenario to consider. Because you want to have exactly one letter between you and I, and exactly one letter between A and E. Are there 2 scenarios, 3 scenarios, or just one scenario?
There is more than one scenario.
More than one scenario. Okay. So let us try to understand that one scenario. I would think in this problem, because I want to have exactly one letter between you and I, the simplest scenario comes to mind is to have a box, within the box 3 empty spaces, okay, and then the first one and the last one should be dedicated to either you or I, and some other letter in the middle, yes? So I will call it, I don't know what is a good name, I will call it UI box. UI box means the box containing you and I with something in the middle. How can I construct this box? How many possibilities are there to construct this box? These 2 will be dedicated to either you or I. So how many options I have to put my UI there? 2, yes? I have 2 options. Either I put you here, I there, or the other way around. Okay, let us say that I chose to put I here and you there. But this box is still not accomplished. I need to have a letter there. Okay, but that letter, I will not choose them from A and E. Okay, for the time being. Okay, so how many other letters are there? U is already used. I is already used. A and E are not allowed to be used here for the time being. So how many options are there? 1, 2, 3, 4, and 5. So I have 5 options for putting a letter there. Okay, so one of those letters, let us say L, is also eliminated. Let us say that I chose L to put it there. But be careful. This number is independent of how I arrange these 2, yes? No matter in which order I put them, this 5 is independent of how it's done. So there are 10 ways to construct the IU box. But let me construct another box, which we call it AE box. For constructing AE box, what should I imagine? I imagine the same thing, yes? I have 3 empty places here. Either A should be here, E should be there, or the other way around. So because of that, I have a 2 here, yes? But let me choose A to be here, E to be there. So how many letters, I need another letter to put here. So how many letters are left for me? N is left 1, 2, and 3, and 4. So this time 4 letters are left. So if I ask you, what is this 10? 10 is the number of ways that I can construct my UI box. 8 is the number of ways that I can construct my AE box. Let me choose V here, for example. Okay, V is also gone. So, but how many letters are left? So let me count, everything is right. 1, 2, 3, 4, 5, 6, 7, 8, 9. I have used 6 of them, so 3 of them are left. So there will be 3 more letters involved. Yes? But then I need another what factorial? Because I can actually start permuting these items. One item, second item, third, fourth, and fifth. These are different items. I want to permute them. So what do I need? I need a 5 factorial at the end. Yes? So this is one scenario. So let me just multiply them. 4, 20, 80. So this is just 80 times 5 factorial. Okay, but this is not the only scenario. Yes? Do you agree? This is one possible way that I constructed permutations in which there is exactly one letter between them, between U and I, and there is exactly one letter between A and. What is the other scenario that you imagine? Yes? Yeah, somehow they, oh yeah, so exactly. So the letter that I am going to put between I and A, U, should be one of these other letters that have some constraints, A and E. So this time I consider one box with how many places? 4 places, and I will call it UIAE box, for example. Okay? But I have to arrange them in a way that I have to respect the condition of the problem. So there are 2 alternatives. For example, these 2 places could be filled with U and I in any way that I like. And then these 2 places will be filled with A and E in any way that I like. Yes? But this is not the only way. I can start with A and E here and U and I there. Okay? So if I want to consider this, how many options I have? Let me write 2 options for which one should come first, which one should come second. Yes? Because I have 2 alternatives. Do you understand what I mean? Because I can start with the combination UI here, for example, and AE here. This is one possibility. Of course, I can start changing them. I can also changing them. Still, I am respecting the condition. Yes? But I can start with A and E here and U and I there. These combinations I have to consider. So 1, 2 is because which one I prefer to start with. Do I want to start with UI pair or do I want to start with AE pair? That is that too. Okay? Now I decided, let us say I decided to start with UI pair. And now I want to put my UI pair there. So how many options are there? Again 2. Okay? And then I want to fill up the rest with AE pair. And how many options are there? There is another 2. Is that right? Now, for the time, I have constructed this box. Okay? Which respects the conditions. But how many options are left? So 1, 2, 3, 4, 5, 6, 7, 8, 9. 4 of them are used here. So how many items are left outside? 5. Yes? And now how many objects you see? You see this box and 5 more letters. So in total, how many objects you have? 6. So you have to multiply it by an extra 6 factorial. Do you agree? Okay, so the answer to this becomes 8 times 6 factorial. But 6 factorial, because this is 5, let me write it as 6 times 5. So it becomes 48 times 5 factorial. Yes? And then the answer to the question mark should be the sum of these 2 numbers. But this is 85 factorial, this is 48. If I add them up, it becomes 128 times 5 factorial. But then probably we will need the calculator or whatever. So this is 100. we don't need calculator because this can be written as 120 plus 8 multiplied by 120. This I have it in my memory. 12 times 12 is what? 144. So there are 2 zeros. And this one is just 960. So the answer becomes what? The answer becomes 0, 6, and then 350. So 15,360. Of course, I have given you access to the calculator, so you don't need to be worried about calculating the numbers. But is the idea clear? Yeah, so you have to consider sometimes different scenarios. Yes, please.
But the idea of coming up with this, like, how
No, it is not very hard, by the way. Let us look at this as a game. You really can think about it. It is not hard to think about it. No, it is not hard to think about the scenarios. Might be you have some troubles or you make some mistakes in calculating the right item. But you really want to consider that I want to do the job. I think everyone's brains will consider these two cases. These are the only two cases. But I agree, because when I come up with a scenario, might be it is not easy to come up with the number of possible ways to do the scenario. That is the hard part. Usually coming up with the scenarios are not hard unless there are there are a lot of possibilities that I have to make sure that do I really care about all possibilities or just I am ignoring some of them. But I don't think that was very hard to come up with.
is
Yes.
it possible to use Venn diagram to solve it?
In principle, you should be able to do it when it comes with complement principle or something, not by the product principle. Yes. Yeah. Okay. Any questions? Okay. So let us go to the next problem. So this one was correct. Yes, 15,360 possible cases. Okay. So yeah, this was very simple. So in principle, you should be able to really do this one yourself. I don't know why I put this number 4 because this is probably that is not very important to have this question again in this homework. But anyway, could you do it now yourself? In how many permutations of the word flexicam are no two vowels adjacent? But how many vowels are there? 3. So just we talked about that, if you remember a little bit. I think it was in problem 2. Yes? Okay, could you do it? This is just exactly the problem I just told you. Yes? So how do you solve the problem in the elegant way? But for this one, just for mathematical curiosity, I want to solve the problem using the complement rule. I want you to see how complicated it becomes. Okay, so I want you to see it because at least that's an experience. This is also something that people will learn later. It's called inclusion-exclusion principle. So if you generalize the idea of complement principle, this will be what I will talk about it a little bit later. But let us do it in the standard way. So this is this might be a high-level question, but because you already know the method, it's very simple. It's not a hard one, yes? So none of these are supposed to be adjacent. So it means that these vowels, E cannot be next to I cannot be next to A. So none of these things could be adjacent. So what do you remember? I told you that. Forget about those letters with constraints. So what are letters left? A is gone, I is gone, E is gone. 1, 2, 3, 4, 5. So I start arranging them in how many ways I can do that? 5 factorial ways. So let us say I chose to put L here, I chose to put M here, C here, and then what are the other one? F here, X here. This is one possible way of arrangement. But then what was the idea? The idea is to look at the spaces between them, yes? So how many spaces I have? I have location number 1. So let me write it. So let me start from this side. Location, capital X1. This is my box 1. So let me write box 1 to remind you of that. Box number 1, box number 2, box number 3, box number 4, box number 5, and finally box number 6. Yes? Then how many marbles I have? I have 3 distinct marbles. I have 6 distinct boxes. I want to distribute the marbles within these boxes in a way that every box receives at most 1 marble. And that is exactly the standard abstract model we have. So what is the answer to that? Is P, the number of boxes is 6, the number of marbles is 3. So that's the answer. Yes? So if you answer this problem, so it becomes 5 factorial. So this is 6 factorial divided by the difference between them, which is 3 factorial again. So this becomes 120. I have it in my memory. This is 720 divided by 6 is another 120. So you don't need even the calculator in principle. That's the answer. Yes? Is that right? But let me also teach you, this is just a mathematical curiosity, how you imagine using the Venn diagram. Because whenever you want to use complement rule, somehow, it is better to have the Venn diagram. So I want you to see that in the cases that I have constraints only on 2 objects, the complement method was more or less equivalently hard. It's not harder, yes? But if it becomes more than 2, then you are in trouble. Let us see how. Let us imagine that in this rectangle, this is the universal set. Here the universal set is the set of all permutations of this word. I put them in this rectangle. In some of them, A and E are, so E and I are adjacent. So let me call it A. So A, E, and I adjacent. Yes? And B, let us say E and A adjacent. And C, let us say that E, A, and I adjacent. Okay, from your perspective, how do you think I should draw these circles? I should draw them separately within one another, or how? For example, don't get confused. Just say that I want to draw B. Should I draw B outside? Should I draw B inside? What? Yes? Yes, because it is not guaranteed that everything in B is in A or everything in A is in B, but there is guaranteed that there is an overlap. What is the meaning of the overlap? It means that not only A and E are adjacent, but A and A are also adjacent. This is possible. For example, if I have A, E, I. Some of the items are like that. And if I want to draw the circle for C, how do you think I will draw it? For the same reason, that circle C should have the same situation with respect to A and B. Is that right? Because that's the same idea. So I have to draw circle C like this. Is that right? So this is the idea behind this. Now, where I am interested in now, which items I want to count? I want to count the number of items outside all these circles. Because if I am within one of these circles at least, the corresponding letters are next to one another. So if I want to answer the problem, I need to count the number of items outside this 3 circles. Is that understandable first? Okay. But if I want to do that, do I know the total number of items there? I know. The total number of items is the total number of permutations. So 1, 2, 3, 4, 5, 6, 7, 8. So if I consider my universal set, I already know the cardinality in the universal set. What was that? 1, 2, 3, 4, 5, 6, 7, 8. Yes? Am I right? Please check my calculations. That's 8 factorial. But do you remember we had something in set theory? Do you remember? If I want to count the number of elements within these circles, okay? This means that I am interested in the cardinality of the union of all those sets. Do you remember? I don't know how many of you remember. We had a formula for this. So it was this. It was the cardinality of the first one plus cardinality of the second one plus cardinality of the third one, minus the cardinality of A intersection B, minus the cardinality of B intersection C, minus the cardinality of intersection C and A, plus the cardinality of A intersection B intersection C. So that was the formula. Yes? Okay, but let us do it for practice. So this is a formula. If you have forgotten, you can go back and see that we had it in set theory. In the book is one of the exercises. But that is what we had. Okay, do you agree that if I calculate this cardinality, it means the total number of items within these region, and I take it out from this, it will be the number of outside items, yes? And that's exactly the question mark. So this is somehow, the idea is a still complement rule. Could you feel it? I want, this is the total number of items. This is the total number of items that I don't like. I want to take it from that. What is left is what I like. But the problem is that I have to consider a lot of things now if I want to use the complement, if I insist to use the complement principle. Okay, now let us do this problem together because that should be a standard problem. So let us do it together. Let us concentrate here. I want to have cardinality of, I want to count the number of cardinality, the cardinality of A, the number of items in which E and I are adjacent. Again, this is a standard model. You should be very quick in it. So E and I should be adjacent. So I make a box. How many ways I can make this box 2 factorial? And A and I are left. 6 other items are left for me. So I have to, in total, how many items I have? I have 7. Is that right? Because if I took E and I out, there will be 1, 2, 3, 4, 5, 6 letters here. Of course, distinct letters. These 6 distinct letters together with this box becomes 7 distinct boxes, 7 distinct objects. So I have to multiply by 7 factorial. So if I ask you what is this cardinality, what do you say? You say 2 factorial times 7 factorial. But it is a little bit easier. Can you tell me what is the number, what is the cardinality of B? The same, because the letters are 2, but different letters. So I have to, I have another one, 2 factorial times 7 factorial, and I have 2 factorial times 7 factorial. This is for that. Okay? Is that right? But now, can you do this one for me? What is the interpretation? The cardinality of A intersection B. It means that it is somewhere within both A and B. So it means E and I are adjacent. E and A are also adjacent. So can you see how we can count this one now? So E and I adjacent. And then what? E and A also adjacent. Yes.
Become a box that contains all 3 letters, the E and I and A.
Okay, but you have to be a little bit careful. For example, if I want to have a, yes, this is clear. I have to have a box with all those elements within that box. Okay, but is there any kind of arrangement there is okay?
E has to be in the middle.
What? E has to be in the middle. Exactly. Yes. So it should be in a box, but E should be in the middle. Because if E is not in the middle, so what happens? If E is here, then I will have I and A here. Then I have to. Then, of course, I and E are adjacent. I am respecting this condition, but I'm not respecting this condition. So E has to be in the middle. Very good. So this means that in this box that I want to construct, let me call it AEI box. In the AEI box, what should I have in the middle? E. So it should be one scenario there. And then for this one, I have 2 options. But for this one, again, I have 1 option. Is that right? So in how many ways I can construct my EIA box? 2 ways. Okay? Now I put them here. So I have 2 ways here. So be careful. This is minus. So I would write 2. But then how many other letters are left for me? 5 more letters. Those 5 letters together with this box is how many items? 6 items. I want to arrange them. So it becomes 6 factorial. Yes? But do you agree the next one and the next one will be the same? Yes, because there are different letters. So I multiply this by 3. Yes? The last one. The last one is E and I should be adjacent, E and A should be adjacent, A and I should be adjacent. Yes?
You can do that simultaneously.
You cannot do that simultaneously. So the number of items there is 0. You cannot have those three together. Yes? So this means that this drawing is probably not a good one. Or is it? So can you imagine a case, or might be I am wrong, can you imagine a case that EI are next to one another? So if A, let me write EI. And then I want to put A. Either I should put A here or here or here. These are not other cases, yes? If I put A here, is it acceptable? No, because AI are not adjacent. Yes? If I put A in the middle, is it acceptable? No, because E and I will not be adjacent. If I put A here, is it possible? No, because again, A and E are not adjacent. So it means my drawing is not probably correct because it is considering somewhere in the middle. Anyway, we have realized that the next number is 0. Yes? But let us just for fun calculate this. So 2 factorial is 2, 1, 2, 3. So it becomes 6 times 7 factorial minus 6 times 6 factorial. Yes? This is plus 0. How can I calculate this? I borrow 1, 7 and give it there. So it becomes 42 times 6 factorial minus 6 times 6 factorial. So this becomes 36 times 6 factorial. Yes? Okay, what is the question mark now? The question mark is 8 factorial minus what? This number. Yes? I'm not sure. Let us see if it works or not, because the logic we are following is actually correct. So, for example, this one I can write 8 times 7, 56 times 6 factorial minus 36 times 6 factorial. So this becomes 20 times 6 factorial. But 6 factorial is 720, and you multiply it by 20. So what is the answer? That's also the correct answer. But which one do you really prefer? So that's why I'm saying, at least now this is a good thing to learn, that if you insist to use the idea of the complement rule in a correct way, you have to do it in this way. And it is possible. By the way, this is also a very important trick in combinatorics. This way of doing things is called inclusion-exclusion principle. If someone asks you what is inclusion-exclusion principle, is exactly the complement rule generalized for more conditions. Okay, so you have to, why it is called inclusion and exclusion? Because you include these ones, exclude these ones, they're going to include these ones, alternating them. Yeah, that's why it's called exclusion-inclusion principle. So now I hope that you really appreciate this method. Yes? So it is very elegant. For the case of 2 items, that was not a big difference. But for the case of more than 2 items, that one is actually not a good idea. So, but do you know how should we draw the circles now? How should I draw the circles? I should draw them in a way that they overlap pairwise, but not all of them together. How can I draw that? Yes? Is that possible? So you mean, for example, this is very clear that A should be like this, okay? B should be like that. But C should have intersection with A, should also have intersection with B, that is clear. But it shouldn't have here. There is no circle doing that service for us. So you have to draw it something like this. Okay? So I don't think a circle can do the service for us, because then you have to have something like this cookie or something like that. So, but this is understandable now, yes? If I could see it in the beginning, then I should have drawn it in that way. Because still, A should have intersection with B, A and B have overlap, A and C should have overlap, B and C should have overlap, but there should be no overlap between all those three. Yes, please. No, but I don't think it is possible, is it? So let us see how you are thinking. So let us say which circles I have to make it small or big. A, I draw a circle. Okay, B, do you want me to do the same B? Okay, so B is here. Okay,
That's the thing. If you do them very closely, you won't see the space in the middle. You have to, like, the overlap has to be smaller.
it's smaller.
That's
Okay.
why it'd be easier if you draw a very large set.
Okay, so let us say like that.
Yeah.
But how can I? Okay, you mean this circle? Yes, this circle. You mean?
Yeah, you see the space in the middle.
Yes, you are right. Good practice. Yes, that is also possible. So by circles, it is also possible. It's stupid from my side. Yes, this is a very weird shape. Yeah, sometimes it happens. Anyway, so that was a good exercise. At least you can feel now why this method is much better. Okay. Now let us go to the next problem. The next problem is more or less very simple because I just gave this problem because I want you to understand they can ask you questions in which you are not supposed to count anything. They want to actually evaluate your analytic skill, just algebraic skill. So here in this problem for the natural number n, we know that this relation holds. We want to find that n. Okay? So that is just solving an equation. So if you don't know anything about the counting, but you have access just to the formula, you should be able, in principle, be able to solve this problem. Okay? So let us do this together now. Okay, so how can I solve the problem? The problem is solving an equation in principle. So 2pn and 2 plus 50 is equal to p of 2n and 2. Okay, so you know the formula. So I would write it as 2. What is the formula for p? This number, whatever it is, factorial goes to the numerator. And this difference between them, factorial in the denominator. So I'm just using the formula here. 50 is just my constant. I will use the same formula here, but this time 2n is playing the role of n. So 2n totally factorial goes to the numerator. The difference between them, factorial, goes to the denominator. And then I have to simplify this, yes, to be able to solve it. And the simplification is very simple, yes? So I write 2. Instead of n factorial, I write n times n minus 1 times n minus 2 factorial and divided by n minus 2 factorial. Then I have 50 here. On the right hand side, what do I have? I can write it as 2n times the previous number, which is 2n minus 1, times the previous number factorial. Yes? And then divided by 2n minus 2 factorial. And I think it should be obvious to you that why I stop there, because I don't need to go further. This one and that one are cancelled. I get 2 times n minus 1 plus 50. On the right hand side, this one and that one will be cancelled. So it becomes 2n times 2n minus 1. And for simplicity, because everything is divisible by 2, I divide everything by 2, so it becomes n minus 1 plus 25 equals to n times 2n minus 1. And that is an extremely easy problem, yes? I multiply n in. Okay, this minus r, this and that are gone. I move n squared to the other side, so 25 becomes n squared. In principle, n has 2 solutions, plus or minus 5, but you know that because n appears here inside the p permutation, n should be a natural number. So the negative one is not acceptable, so you have to write only n equals to 5. Is that right? Okay, so that was also simple. We just put 5 here. The next problem, let r and n be natural numbers such that r is somewhere between 1 and n. If this relation holds, then the natural number x in terms of n is equal to what you're supposed to. In principle, you are supposed to find this x. Okay? But of course, you shouldn't expect to get x as a number because they have mentioned write x in terms of n. Okay, so That is also something that you can do it, but I want to use this as an excuse. Do you remember I told you that there are some proofs in combinatorics? They are called storytelling proofs. They are very interesting. After we found that, let me also talk a little bit about that. These are good things to know when you have finished this Ma5 course. Of course, I will not ask these things in the exam, but it is good to have heard about them. Okay, so first of all, let us do it algebraically, completely, as if I want to use algebra to solve the problem. So here, P and an N and R plus R times P of what? N and R minus 1 equals to P of X and R. And I'm looking for X. I think you know how to start. There is nothing I can do if I want to solve the problem analytically, and that is just opening it by the formula. What is the formula here? Standard formula, n factorial, the difference between these numbers factorial in the denominator. There is an r here, and then I would write it as what factorial? This number n is playing the role of the n. Of course, it goes n factorial, but the difference between them is n minus r plus 1. So that one goes to the denominator, yes? Factorial of that one will go to the denominator. And this one, what is it? This one, x plays the role of n. The difference between them, x minus r factorial. Or if you want to, let us keep it like this. Because, okay, let us simplify the left-hand side. Can you simplify it? If I have two fractions and I want to combine them, I have to find the LCD, the least common denominator. But what is the least common denominator? Don't multiply them. Of course, multiplication is always working, but it is not always the optimal way. And that is always a common denominator, but not the least common denominator always. Because this one can be viewed as n minus r plus 1 multiplied by the previous number factorial. So it becomes n minus r, because the previous number to this is n minus r factorial. Now you can immediately, this one itself, which is equal to this, can play the role of LCD. Because it is not only divisible by itself, but it is also containing this factor. So if I want to solve the problem, I will take this combination as my LCD, which is nothing except this one itself. And then I compare this LCD with this denominator. I have that extra factor. That extra factor should be multiplied by the numerator there. So it becomes n minus r plus 1 times n factorial, yes? And then plus this compared to this has no extra factors, so it means that I just copy and paste the numerator. But remember, there is a factor of r here, so this becomes r times n factorial. Okay, but how can I simplify that? N factorial appears here and there, so I can factor it out. So it becomes n minus r plus 1. This is left from the first one. N factorial is pulled out. And what is left from here? Plus r. Okay? And now, if you don't mind, let us write this backward. Because this served the purpose, let us go backward. So instead of writing this again, I write this one again. And if you don't mind, let me factor a minus sign. You will see why this will happen. Or might be, no, let us keep it. Not jump ahead. N minus r plus 1 factor. But now what is happening here? This minus r and that r are gone. I am left with n plus 1 times n factorial divided by this combination. But I want to wait for you. What can I do for the numerator? N plus 1 multiplied by n factorial can be written as what? N plus 1 factorial. And then in the denominator, for the time being, there is nothing I can do. There is something I can do, but let us leave it like this. But then, this is the most thing I can do probably. And I want to write this in this form. Okay? But I already see that r should appear there. So can you guess what x is then? What is x? Because you know that this, on the other hand, is x factorial divided by the difference between them factorial. So it has that structure. Yes, I have one factorial divided by another factorial. So it is not hard to see what is playing the role of x if the problem is supposed to be correct. Yes? N plus 1. But is it the case for this one as well? Yes, because you can imagine that as n plus 1 factorial, instead of writing n minus r plus 1, you can write n plus 1 minus r. It doesn't matter. Yes? Now you can compare this with the standard formula. So it is easy to see what is playing the role of x, n plus 1. So this means that x is n plus 1. Is that right? So this is also a famous identity in combinatorics. Some people even remember it. Okay, so, but let us now, is there any questions here? So this is just analytic work. I mean, these are simplest possible questions in combinatorics. These counting ones are the hardest ones. Okay, so at least at the level of your course. But let me write this formula for you and try to prove it using a story. Because we were able to prove this identity. Yes? But let me tell you what do I mean by storytelling proving. I will give you a story about counting something, but I will do it in two different ways. And the idea is that because I am counting the same thing in two different ways, those things should match, if of course I don't do any mistakes. My story is this. Let us say that there are n plus 1 students in a class. Imagine you have n plus 1 students in your class and you have r projects available. Project number 1, project number 2, up to project number r. But of course, r is less than n according to the assumptions in the problem. Okay? So I have n plus 1 students, which are more than the number of projects, but I want to assign the projects to these students in a way that every project is done by exactly one student. Is the question clear? So I want to, in other words, for each project, I want to choose exactly one student. For example, I can write a student 1, do the job number 1, a student do project number 2, and a student number r, project r. I can have those students the same from S1 to SR, but for example, I put S2 here, meaning that student number 2 is supposed to do project number 1. This is a new scenario. Okay? So I want to consider all possible cases. Immediately you should be able to answer in how many ways the teacher can distribute the projects. Every project should be done with exactly one student, no more. So what is this? Is very standard. These are marbles, these are boxes. I want to distribute the marbles within the boxes. In how many ways I can do that? P, the number of marbles, and the number of boxes. So the number of ways that I can distribute the projects among the students is this. Okay? This is one side of the story. But there is another side to this story. Do you agree that in these kinds of distributions, either this student is involved or not involved? Is that clear? There are no other scenarios. Okay, so if I count the number of ways that this student is involved and count the number of ways that this student is not involved and add them up, it should give me this number again. Is that right? This is the story. Okay, the story was distributing projects among students in the way that I told you, and there are two sides for this story. One way, do it in a simple way. This is the number of ways I can do it based on what we learned. But let us concentrate in one of those students. these distributions are definitely in either one of these ways. Either this student will be involved in this project doing or not involved. The number of ways this student is involved plus the number of ways that this student is not involved together should be the number of ways that this project can be done. Is that right or not? Could you feel it or not? Say yes or no.
Yes.
Okay. Okay, but now let us ask you to do it for me. The number of ways that this person is involved. Or let's do it this one. The number of ways that this person is not involved. This is simpler to do. In how many ways I can do the same job, distributing projects to students, but this student is not supposed to be involved. It's very simple. This student is not involved, sorry, you just go away. And how many marbles are left? Yes? P, N, and R. Do you agree? Because if this student is not supposed to be involved, I put it out, and then how many marbles I have, and how many boxes I have, R, so I distribute them. So this is the number of ways that this student is not involved in this project doing. But now, can you tell me how many ways I can give a project to this guy and make him involved? Yes? Oh, yes, but that is not the logic. The logic is I want to count it not by the difference. Because I want to count this on the one side and I have this answer on the other side, and then I want to equate them and prove this by storytelling without doing any analytic work. Now, forget about this. Let me ask you a question, the question again. This time, I want to distribute projects to my students, but I insist to give a project to this student. This is the question. Forget about everything. Just think about this problem. In how many ways you can do that? First, you decide about the project that you want to give to this student. In how many ways you can give a project to your student? Let us say I like it. Okay, I like him or her, and I want to keep him involved. So, what? Yes?
P of n and r minus.
No. No, I'm talking about, so you are thinking probably different things. In how many ways I can assign one project to this person? Or, yes? Because I would say that, okay, I want to keep you, don't say anyone, I want to keep you involved, okay? But then what I'm saying is that I want to give you one of these projects, okay? In how many ways I can assign a project to this student? Or ways. Now, let us assume that this project is assigned by this person. And then the rest of them, I will do it normally. Okay? How many students are left? N students are left, so N marbles are left, but how many boxes are left? R minus 1. Then I will distribute those N marbles within R minus boxes. So this is the number of ways that this person is involved. This is the number of ways that this person is not involved. So if I add them up, it becomes the total number of ways. And this is, on the other hand, should be equal to this one. So these two are the same. So without doing any analytic work, just by telling a story, we understood that this number should be equal to that number. Is that understandable or not? So these are very common. Okay? For example, one of the the time is finished, sorry. Okay, we'll stop here, but there is something that we talk about later. So this storytelling proof is a very nice way of proving. It's a proof. Some people think that this is not a real proof. No, that's a real proof because we counted the same number of items in two different ways. They have to match. Yes? Okay, thank you very much.